Howdy, welcome to Elementary Statistics. I am Lance Curtis. This is the lecture for section 4-4, Counting. So here in this lecture, we're going to talk about factorials, permutations, combinations, which are different ways of getting our sample space, especially when the sample space is really, really large. Up until now, we've been dealing with sample spaces that are fairly small and that are pretty easy to calculate because they're fairly small. The real world, however, is filled with many sample spaces which are humongous, and so we need ways to calculate them easily, and that's what this section is all about. So the big obstacle for many probability problems is finding the total number of outcomes. What's our sample space? So as I said, we're going to look at several methods for figuring out what that sample space is without directly listing and counting all of the possibilities. First, let's encounter some special rules. So first we have the fundamental counting rule. This says that for a sequence of two events in which the first event can occur in m ways and the second event can occur in n ways, the events together can occur a total of m times n ways. This is the fundamental counting rule. Essentially, you've got a sequence of events and each event can occur in a certain number of ways. Well, you just list the number of ways that each of those events can occur, and you multiply the numbers together. That's the fundamental counting rule. Then we have the factorial rule. The factorial rule says the number of different permutations or order counts of n different items can be arranged when all n of them are selected. Basically, what this is saying is that we're selecting the first item in n ways, and then the second item is being selected in one less way, and then the third item is being selected in one less way, so on and so forth, until we've selected all the items. We use an exclamation point as the factorial symbol, and this denotes the product of decreasing positive whole numbers. So, for example, let's say we have 4 factorial. Well, 4 factorial is simply 4 times 3 times 2 times 1, which when you multiply those numbers out, you get 24. Likewise, if I had 3 factorial, I would say 3 times 2 times 1, which is 6. My special definition, 0 factorial is equal to 1. So 0 factorial is equal to 1, 1 factorial is equal to 1, 2 factorial is equal to 2, 3 factorial is equal to 6, 4 factorial is equal to 24, and so it goes on up the chain of integers. Let's look at an example in which this can be used. So let's say a history pop quiz asks students to arrange the following U.S. presidents in chronological order: Hayes, Taft, Polk, Taylor, Grant, Pierce. Now, these are presidents that most people today have never heard of, except maybe Grant. But most of the others, don't really know them all that well. Those of you who may be a little bit more inclined to history may know something more about one or more of these other presidents. In any event, let's suppose that we have a totally unprepared student. So someone who didn't study at all, someone who has no idea when any of these presidents were in office, and so therefore has no idea of how to place them in chronological order. What is the probability that this student will guess the correct answer? Well, first we got to find our sample space. So the possible arrangements that we have are, we've got 6 presidents to choose from. So there's 6 names for the first placement, the one who served first. Then once we select that president, there are 5 left to choose for the second spot. And then once we choose that name, then 4 are left to choose for the third spot, so on and so forth. So we have 6 times 5 times 4 times 3 times 2 times 1, which is 6 factorial, which we punch that out on our calculator and we get 720. So we have 720 different arrangements in our sample space. The probability of then guessing the one correct answer out of the 720 possible arrangements is 0.00139, or 0.139%. So we've got about a 0.1% chance of actually guessing this right if we know nothing about any of these presidents. Now let's shake it up a bit. Let's suppose that the student recognizes that Taft is the only president in this list to serve in the 20th century. All the other presidents served in the 18th century. The 19th century, during the 1800s. So, with this one piece of information, what now is the probability of guessing the list correctly? Well, we know that Taft is going to go last, so that means the possible arrangements leave us with 5 names for the first position, 4 names for the second position, 3 names for the third position, 2 names for the fourth position, and then there's 1 name left for the 5th position because we know that Taft goes last in that 6th slot. This then is 5 factorial because we have 5 times 4 times 3 times 2 times 1, and then anything times 1 is itself. So we're left with 5 factorial, which comes out to 120. So the probability of guessing the one correct answer with this one piece of information is now 0.00833 or 0.833%. Now, by itself, you may be saying, that's still not great. We're not even over 1% yet. But look at the incremental improvement with this one piece of information. We've increased our probability of guessing correctly by a factor of 8. So, let this be a lesson that the math is teaching us that any little piece of information we can get to help us in a test is actually well worth it. The probability will increase with the more information we have. Let's talk about permutations and combinations. Now, the way you know that you need to use one or the other is by asking a key question. And that key question is this: does the order matter? If the order of the sequence of events matters, then you want to use permutations. If the order doesn't matter, then you want to use combinations. So when the order matters, use permutations. However, if you know you need to use permutations, the particular equation you're going to use is going to be different depending upon whether or not some of the items in your sequence are identical to each other or if they're all different. If all the items are different, so you don't have any repeating items in your sequence, so you're going to have n different items, selecting r of the n items at a time without replacement, and again, considering rearrangements of the same items to be different sequences. So the sequence ABC is counted as a different sequence than CBA simply because the order matters. So you've got the same elements, but they're in a different order. So you're counting them as a different sequence because the order matters. In this case, you want to use permutations. Here's the formula for calculating permutations of n items taken r at a time. You take n factorial and divide it by the quantity of n minus r factorial. This is your formula for calculating permutations. It's the number of possibilities for your sequential order when the order matters. When some of the items are identical to each other, then you're going to use a different equation. And this is the equation that you'll use. You'll take n factorial on top, but then on the bottom, you're going to take n1 factorial, n2 factorial, nk factorial, and these are basically factorials for each of the different items that are repeated in your sequence according to the number of times that they're repeated. Let's look at some examples to illustrate how each of these different equations are used. So let's look at a touring rock band to start with. So a rock band on tour wants to maximize their profit by choosing the most efficient route. What route will bring them the most money in the least amount of time? They have 12 venues that are available, but they can only schedule 7 of them. What then is the probability that a randomly selected route will be the most efficient one? Well, first we need to calculate our sample space. And here is where the permutation comes in. We ask ourselves the key question, does the order matter? Well, if we want the most efficient one, yes, the order will matter. Because if we mess up the order, so something different, then it's going to be less efficient than the most efficient one. There's only one most efficient order, and so that's the one we're looking for, and therefore the order matters. So we're going to use permutations because the order actually matters. Note there's also no repetition in the sequence. So that means the permutation equation we're going to use is this one right here. So we take the 12 cities, which is our total. We're taking them 7 at a time. So 12 minus 7 in the denominator leaves us with 5 factorial. So we've got 12 factorial divided by 5 factorial, which we punch that out on our calculator and we get 3,991,680. This is our sample space. Now we know the total number of possibilities in our sample space, we can calculate the probability of selecting the one best route, which is just 1 over 3,991,680, which is a really small number. It's not likely you're going to pick the most efficient route by random selection. Is it practical then to list all the different possibilities in order to select the best one? Well, given that there's almost 4 million of them, I should think not. That's not very practical. The total number is very large. I mean, how many sheets of paper are you going to need? Even if you have very, very small print, it's going to take you many sheets of paper to print off each of the different possibilities. There's almost 4 million of them. So no, it's not very practical to list them all. You're going to want to try to identify the most efficient route by some other means. Here's another example involving the arrangements of letters in a word. So some problems are asking you about the number of ways you can arrange the letters in a given word. For example, how many ways can the letters in chocolate be arranged? The first step is to count the number of letters in the word. So how many letters does the word chocolate have? I'll give you a moment to count. You should have found that chocolate has 9 letters in it. Now, the second step is to identify how many of those letters are repeated and how many times those repeats occur. Again, I'll give you a moment. Well, here we see that the letter C is repeated twice, and the letter O is also repeated twice. So now we have the information we need to set up our fraction that we're going to use to compute out the number of ways we can rearrange the letters in the word. So that's our third step. Set up the factorial fraction with total on top and repeats on the bottom. So when we do that, here's what we get. The 9 factorial on the top accounts for the total number of letters in the word. Then we have 2 factorial on the bottom repeated twice. The 1 factorial on the left, 2 factorial, accounts for the repeating C. The C is repeated twice, therefore it's 2 factorial. The other 2 factorial accounts for the repeating O. It also repeats twice, so therefore it is 2 factorial. Now let's suppose we had a word in which the letter C was repeated twice and the letter O was repeated 3 times. Then on the bottom of our fraction we would have 2 factorial times 3 factorial because the C is repeated twice and the O is repeated 3 times. Once you set up this fraction, then it's just a matter of punching it down on your calculator. And when we do that, we find the number 90,720. This is then the number of possible ways we can rearrange the letters in the word. Of course, if the order doesn't matter, then we're going to use combinations, and we're going to calculate them according to the formula that you see here at the bottom of the screen. Note that when you're calculating for combinations, again, the order doesn't matter. So rearrangements of the same items, even though they may be in a different sequence, they're going to be counted as the same sequence because the order matters. So ABC will count the same as CBA, BCA, BAC, and CAB. Order doesn't matter, and that's why we're using combinations. Now, if you look closely at this equation, it looks a lot like the equation we were using for permutations. And in fact, it's exactly the same, with one minor but very important difference. In the denominator of this equation, we have an extra term, r factorial. This extra r factorial is what makes the difference between combinations and permutations. Let's look at an example where we would use this. In the Pennsylvania Max 6 Lotto, winning the jackpot requires selecting 6 different numbers from 1 to 49. The winning numbers can be drawn in any order. Now, with that right there, you know the order doesn't matter. Therefore, you're going to use combinations and not permutations. Question is, what is the probability of winning if just one ticket is purchased? First, we have to get our sample space. We know the order doesn't matter, so we're going to use combinations to do it. So here we go. Here's our formula for combinations. We're going to plug in for the n and the r. The n is the total number that we can choose from. So there's 49 different numbers we can choose from. And the r is how many we take at a time, which is 6. So the combination of 49 items taken 6 at a time will give us 49 factorial on top, and then 43 factorial times 6 factorial on the bottom. The 43 comes from our n minus r, which is 49 minus 6. We punch this out on our calculator and we get 13,983,816. This is the total number of possibilities that we have for arranging ranging 49 different numbers that we take 6 at a time. The probability of then selecting of purchasing one ticket that has the win is 1 over 13,983,816. Which, when you divide that out, you get a very, very small number. So we can see here that the chances of winning the lottery are not that great. Now, here's an added question for you. How many tickets would we need to purchase in order to have a reasonable chance of winning the lottery? Well, what sort of percentage would you say that you'd have to buy? I mean, I know if we purchase 10 tickets, what's that going to do with our probability? Well, that's just going to move this decimal place over one place to the right. That's still going to give us a really, really small number. So how many decimal places would we have to move this over in order to get a reasonable probability? We're going to have to move it to the right by quite a few decimal places. Would you say 7% is a reasonable probability for winning? I wouldn't. 7% isn't that far away from 5%, which is a threshold value it's that general rule of thumb that we're using to choose between what's high and what's low. So, yeah, it's still around that 5%. I wouldn't say 7% is awfully high. What about 71%? Well, yeah, I'd say 71% is a really decent chance of winning. So, how many tickets would we have to purchase in order to get that 71%? Well, we'd have to move that decimal point over here to the left of the 7 in order to get 71% for our probability. Well, that means we're going to have to move our decimal point over 1, 2, 3, 4, 5, 6, 7 places, meaning we're going to have to multiply this by 10 to the 7th power. 10 to the 7th power is, let's see, it's 10 million. So we'd have to buy 10 million tickets in order to have a decent chance of winning the lottery. Can you see that this is a loser's game? When you do the math, it's really easy to see that conclusion. And I hope that all of you take the advantage of this knowledge that you've now gained. And remember, the lottery is a losing proposition. You're throwing your money away when you play the lottery. Before I wrap up the lecture, I want to take a moment to talk about using your calculator to count calculations. Now, you've probably been looking at the calculations we've been doing in this lecture and thinking to yourself, oh my gosh, I'm going to have to be punching numbers like crazy on my calculator. Because here's the thing, I'm not aware of any functionality in StatCrunch that allows you to calculate permutations, combinations, and factorials. So you're going to have to do this on a hand calculator. Or you're going to have to use Excel, which I'll talk about in a moment. But first, let's talk about the hand calculator. When I'm calculating a number like, say, 23 factorial, I'm not punching into my calculator 23 times 22 times 21 times 20, so on and so forth. That's laboriously tedious. No, I'm using the built-in functionality in my calculator to calculate it out. So here's how I do that. Many calculators will have symbols above the buttons, and these symbols represent alternative functions that you can employ in the calculator. So you want to look at these spaces in your calculator for the symbols NCR, NPR, and X exclamation point. These are the symbols for combinations, permutations, and factorials. So on my TI-30XA that I recommended at the first day of class, these functions appear above the 8 button, the 9 button, and the 3 button respectively. Because they're there in green above the buttons that you normally press, that's indicating that I have to press the second key up at the top left of the calculator in order to activate whatever function I desire. So typically, you're going to enter the value of n first, then you activate the function by pressing second and then either the 8 or the 9 key, depending if you want combinations or permutations, and then you press the number for the R, then you press equals and out it comes. It's beautiful. I mean, you don't have to sit there saying this number times 1 less, times 1 less, times 1 less, times 1. No, you don't have to do that. It's really good functionality, and you need to learn how to do this because it makes life really, really simple. Of course, if you're calculating the factorial, just punch in the number, then the second key, and then the 3, because it's got the factorial symbol over it, and then press the equal sign, and boom, out it comes. Now, I mentioned you can do this in Excel, and here are the functions with the syntax that you need in order to do this in Excel. So fact is the function for factorials, permute is the function for permutations, and combin is the function for calculating combinations. So if you want, you can actually do this in Excel. Just put your cursor in to select one of the cells and type in equals fact, and then put whatever number you want to take the factorial of there in parentheses, and press the enter key, and out comes your answer. So if you're not familiar with how to use your calculator to calculate permutations, combinations, and factorials, I suggest you get familiar with it, because once you know how to do that, it makes life a whole lot easier for doing your assignments in this particular section. That brings us to the end of this lecture. If you have any questions, you know what you need to do. Otherwise, I will see you in the next video. Thanks for watching.